Okay, ready to dive into something you might not expect to find thrilling.
I'm intrigued. Tell me more.
The world of equations.
Okay, I'm gonna stop you right there.
What's up?
That doesn't sound thrilling.
I know, it sounds a bit like, school's back in session.
Yeah.
But trust me on this, we're about to uncover the hidden lives of these mathematical rock stars.
Because it's amazing how often people just think about equations as things in textbooks and they completely miss how influential they are in our daily lives.
Exactly. And our guide for this deep dive is Ian Stewart and his book, 17 Equations That Changed the World.
Oh, great book.
He reveals the fascinating backstory of these equations, proving they're not just dusty formulas, stuck in the back of some textbook. They're the backbone of how we understand and interact with the universe.
And that's what's so great about that book is Stewart's real talent to take these seemingly abstract symbols and to show how they've driven progress in like science, technology, and even the arts.
Let's start with the familiar one, the Pythagorean theorem. A squared plus b squared equals c squared.
Right.
Remember using that to figure out the sides of triangles.
Of course. Yeah, who doesn't?
But what's so fascinating is that this simple equation, we learned this probably in grade school, right?
Yeah.
It's had a profound impact on fields far beyond just basic geometry.
Like, for instance, it's fundamental to understanding the curvature of space-time.
Whoa, think about that.
Yeah.
What started with measuring land for farming now helps us comprehend the shape of the universe.
It really is incredible. And, like your phone, its ability to pinpoint your location on a map, that's the Pythagorean theorem.
Get out. No way.
Yeah, it's essential for technologies like GPS.
Now, that's what I call a hidden superpower.
Absolutely.
And speaking of hidden superpowers, let's talk about logarithms.
Okay.
I'll admit, they always seemed like a bit of a mathematical chore to me.
Yeah.
But Stewart really helped me to see them in a whole new light.
Yeah, logarithms, what's often overlooked is the historical significance of them because before calculators, they were essential for simplifying complex calculations.
And they were crucial for early astronomers like Kepler, right?
Oh, yeah.
He used them to create accurate astronomical tables.
Yeah.
And these tables, by the way, were based on the powers of 1.0000000000001.
Wow.
Talk about dedication. And, without logarithms, Kepler might never have cracked the laws of planetary motion.
Well, yeah, and it's interesting how that's not where the story ends because fast forward to today and logarithms are still essential. Underpinning things like the decibel scale.
How we measure the loudness of sound.
Yeah, exactly.
Right.
Data compression, makes streaming music and sharing photos possible.
So the next time you're enjoying your favorite playlist, thank a logarithm.
Yeah, absolutely.
Okay, get ready for this one because we're about to enter the world of imaginary numbers.
Okay.
Remember that mind-bending concept, the square root of -1?
Oh, yes.
Right.
Leibniz described imaginary numbers as a prodigy of the ideal world.
And he wasn't exaggerating.
No.
They might seem baffling at first, but they paved the way for complex numbers, which revolutionized fields like electronics. It's like they unlocked a secret level of math that we didn't even know existed.
Yeah, and it's a great analogy because it's spot on. Without complex numbers, we wouldn't have the technology we rely on every day.
Wow.
Your smartphone, for instance, it wouldn't be able to process the wireless signals without the kind of magic of complex numbers at play.
That's incredible. They're like the invisible scaffolding holding up our digital world.
Yeah.
Speaking of invisible forces, Stewart takes us on a fascinating journey of how equations even govern something as fundamental as music.
Well, it's all thanks to the wave equation, right? And what's so remarkable is that there's a link between this equation and the musical ratios that were discovered by the ancient Greeks.
Wait, so like Pythagoras?
Exactly. Yeah,
Yeah.
Pythagoras. And it turns out those harmonious sounds that we enjoy, they're actually rooted in mathematics.
Wait, so you're telling me that the same equation that explains the vibrations of a guitar string also explains how sound waves travel through the air?
Exactly. The solutions to the wave equation, specifically sine and cosine waves, are the building blocks of musical harmony.
Get out of here.
Different frequencies of those waves create the different notes that we hear. And it's not just music. The wave equation helps seismologists analyze earthquakes.
It's like this one equation holds the secrets to both.
Yeah.
Like beautiful music and keeping buildings from crumbling during an earthquake.
Yeah, and it's a great example of how an equation can have applications in these seemingly unrelated fields.
Totally.
And it really highlights that interconnectedness of the natural world, you know?
Okay, ready for another equation that sounds way more complicated than it actually is.
Okay, hit me.
Let's talk about the Fourier transform. It might sound intimidating,
Yeah.
but it's a surprisingly elegant concept.
It is.
Imagine being able to take a complex sound wave, like a symphony orchestra playing all at once,
Okay.
and separating it into the individual notes played by each instrument.
Yeah.
That's essentially what the Fourier transform does.
Yeah, that's a great way to kind of explain it.
So it's like a mathematical prism
Exactly.
that breaks down complex patterns into their simpler components.
Yeah, it's like having this like super powered equalizer, you know?
I love that.
And this decomposition of complex signals is what allows us to like store digital photos in smaller files or enjoy clear audio recordings or even experience faster internet speeds.
Okay, so it's like the Swiss Army knife of the digital age.
Exactly.
Now let's dive into something a little less visible. The world of fluid dynamics.
Okay.
Stewart introduces us to the Navier-Stokes equation, which, okay, get this, it governs how everything from water to air flows.
It's a very important equation.
It's the equation that allows us to understand why airplanes can fly, how weather patterns form, and even how blood circulates in our bodies.
It's amazing, isn't it?
So this one equation is essential for understanding everything from, like, the Wright brothers' first flight to modern-day weather forecasting.
Yeah.
That's a pretty wide range of application.
It is, and you know what makes it so interesting is its complexity.
Oh, really?
Because even today, with all of our computing power, fully solving the Navier-Stokes equation for complex situations like turbulent flow, it remains one of the biggest unsolved problems in physics.
Really? Wow. It's a good reminder that even in the 21st century, there's still so much we don't know about the universe and how it works.
It's humbling.
Speaking of big questions and groundbreaking discoveries, Stewart brings us to a pivotal moment in physics. Maxwell's equations.
Yes.
So before Maxwell, electricity, magnetism, and light were all considered separate phenomena.
Right.
But his equations revealed this profound truth that they're all interconnected.
They are.
Different aspects of the same fundamental force, electromagnetism.
It's really incredible.
It's like realizing that three, seemingly separate stories are actually chapters in the same epic novel.
Yeah. I like that. That's a good way to put it because it was a paradigm shift in our understanding of the universe, you know?
Totally.
And it's these very equations that predicted the existence of electromagnetic waves, which we now know as radio waves.
Wait, so you're saying that the wireless technology we rely on today, from radios to Wi-Fi to smartphones, all stems from these equations?
Yeah, pretty much.
Mind-blowing.
It really is. And you know it's a testament to the predictive power of mathematics because Maxwell's equations, they didn't just describe what was already known.
Yeah.
They pointed the way to entirely new realms of physics and technology.
That makes you wonder what other groundbreaking equations are out there just waiting to be discovered.
Oh, no, right?
But before we get too caught up in the future, Stewart brings us back down to Earth,
Okay.
or at least to the realm of population dynamics, with the logistic equation.
Okay.
This seemingly simple equation, often used to model population growth, reveals something really profound about the universe.
Okay.
The presence of chaos. Even with perfectly deterministic rules, the logistic equation can produce unpredictable and chaotic behavior.
Yeah. And you know, it's interesting because we see that in so many different areas.
So you're saying those chaotic stock market fluctuations that have us all reaching for the antass, it's like there might be a deeply mathematical reason for those gut-wrenching roller coasters.
Yeah, there's a distinct possibility, you know, because the logistic equation really highlights that even in a system governed by like seemingly simple rules, tiny changes in initial conditions can lead to vastly different outcomes.
Wow.
Which makes long-term predictions like incredibly difficult.
It's a bit unsettling, isn't it? It's like realizing that even with all our knowledge, there's this inherent element of unpredictability baked into the fabric of the universe.
It's a humbling thought for sure, and it challenges our traditional notions of this like clockwork universe, you know, where everything unfolds in this predictable and orderly fashion.
It's enough to make you want to toss out your financial planner and just go with the flow.
Right.
Speaking of going with the flow, Stewart takes us on this mind-bending journey through Einstein's theories of relativity,
Okay.
where time and space themselves become fluid.
It's amazing. And, you know, Einstein's famous equation EMC2,
Everyone knows that one.
which relates energy to mass, fundamentally changed our understanding of the universe,
Right.
you know? Time is not absolute.
Right.
Gravity warps the fabric of space-time, and energy and mass are two sides of the same coin.
And let's not forget about the whole nothing can travel faster than light thing. It's the kind of stuff that makes your head spin.
It really does, and it's incredible because Einstein's insights, they emerged from this, combination of thought experiments and mathematical equations, and they led to the prediction of black holes,
Wow.
gravitational waves, and even the expansion of the universe itself.
It's like he pulled back the curtain on a whole new level of cosmic reality.
Yeah, exactly.
But just when you think it can't get any weirder, we enter the realm of quantum mechanics,
Here we go.
where things get really strange.
That they do, and our guide through this kind of bizarre and fascinating world is Schrödinger's equation,
Okay.
which is really a cornerstone of quantum mechanics.
Okay.
It describes the behavior of particles at the atomic and subatomic levels.
So like really, really, really small.
Very small. And it challenges everything we thought we knew about how the world works. Because, in the quantum realm, things can be in two places at once. It's just a completely different set of rules.
Right. It's a world where the act of observation can actually influence the outcome of an experiment.
That's right.
It's a mind-boggling concept for
Yeah.
sure, but one that's been experimentally confirmed time and time again.
It is.
And while it might seem like something out of science fiction,
Yeah.
Schrödinger's equation has had a profound impact on our technological world.
Oh, absolutely.
Well, it underpins a wide range of technologies. I mean, from lasers and transistors, which, are the backbone of our computers,
Right.
to medical imaging and even nuclear energy. Wow, so the same equation that describes the bizarre behavior of subatomic particles also enables us to explore the human body, harness the power of the atom, and even, watch cat videos on the internet.
That's right. And it really speaks to this interconnectedness of the universe, right?
Yeah.
From the smallest particles to the technologies we rely on every day.
And speaking of technologies that have revolutionized our world, Stewart takes us on a deep dive into the world of information theory.
All right.
And that's where Shannon's equation comes in.
Okay.
It might not be as famous as EMC2,
No.
but it's had an equally profound impact on our modern world.
Absolutely.
Because Shannon's equation gave us a way to quantify information itself.
Yes.
So we're not just talking about transmitting messages.
Right.
We're talking about, understand the very nature of information.
Precisely, yeah. It's like Shannon's equation gave us a way to measure information content,
Right.
to understand how to transmit it efficiently and reliably, even in the presence of noise, and to, explore the theoretical limits of communication.
So this is the equation that made the digital age possible.
In many ways, yes, because Shannon's insights are kind of woven into the fabric of our digital world.
Oh.
They're the reason why we can compress digital photos and music, the reason why we have error-correcting codes that, ensure the reliability of our internet connections,
Yeah.
and the foundation for the development of modern computers and communication networks.
It's incredible to think that all of that complexity, all of that information flowing around us can be traced back to this one elegant equation.
It is. And, it also highlights this recurring theme that we've kind of seen throughout our exploration of these world-changing equations.
What's that?
The unexpected connections between, seemingly disparate fields of knowledge.
Right.
Who would thought that an equation about information theory would be so fundamental to the development of the internet?
Right. It's like the universe is this giant interconnected web, and these equations are the threads that reveal its hidden patterns and connections.
Oh, like that.
But just when we think we have a handle on things, Stewart throws us another curveball.
He does, because he closes the book with this really thought-provoking discussion of chaos theory, which challenges our traditional notions of predictability and control.
Okay.
Remember the logistic equation
Yeah.
and its chaotic behavior. That makes it come back here, and it illustrates the profound implications of chaos theory.
So we're back to that idea that even in a universe governed by laws,
Right.
there's room for randomness, unpredictability, and a healthy dose of chaos.
Yes, exactly. Because even with perfectly deterministic rules, tiny changes in initial conditions can cascade into wildly different outcomes.
Yeah.
It's what makes long-term weather forecasting so challenging,
Right.
and why it's, nearly impossible to predict the stock market with perfect accuracy.
It's a humbling thought, isn't it, to realize that even with all our scientific advances, there are limits to what we can know and predict.
It's a good reminder that the universe is full of surprises, and that
Yeah.
the pursuit of knowledge is an ongoing journey, not a destination.
Okay, so we've journeyed from ancient Greece to the quantum realm,
It's been quite a ride.
explored equations that govern everything from music to black holes.
And we've seen how these powerful tools have not only unlocked the secrets of the universe, but also shaped the world we live in.
But where do we go from here? What uncharted territories are, mathematicians and scientists exploring with these equations? What's next?
Well, I think that's the beauty of science, right? The quest for knowledge never ends.
Yeah.
There's always some new mystery to unravel, some new frontier to explore.
So what are some of the big questions on the horizon? What mysteries are keeping these brilliant minds up at night?
Well, one of the holy grails of modern physics is this search for a unified theory of everything,
Okay.
a single equation that could explain all the forces of nature.
Whoa. A single equation to rule them all. That sounds like something straight out of science fiction.
It's a hugely ambitious goal, but there are some intriguing contenders out there.
Like what?
Well, one of the leading candidates is string theory,
Okay.
which proposes that the universe isn't made of these point-like particles, but rather these tiny vibrating strings of energy.
So you're saying everything around us is made of these tiny little cosmic guitar strings. That's a pretty mind-bending concept.
It is. It's definitely a radical shift from our classical understanding of the universe. And while string theory is still in its early stages,
Right.
it has the potential to revolutionize our understanding of gravity, quantum mechanics, and the very fabric of reality.
It's like discovering a whole new set of notes to this cosmic symphony we're just beginning to hear.
Exactly, yeah. And the search for this unified theory is just one piece of the puzzle. Because equations are also playing a critical role in tackling some of the most pressing challenges facing humanity today.
Like what? Give me some examples.
Well, for example, in medicine, right? Mathematicians are developing these sophisticated models to simulate the spread of diseases,
Oh, wow.
which can help us predict and potentially prevent future outbreaks.
So equations are becoming our weapons in the fight against pandemics. That's incredible.
Absolutely. They're essential tools in our arsenal, giving us this deeper understanding of how diseases spread and how to intervene more effectively.
That's amazing. What about other fields?
Well, in climate science, equations are at the heart of these complex models we use to understand the Earth's climate system. And these models help us project future climate scenarios, assess the impacts of climate change, and hopefully explore potential solutions.
So we're talking about using equations to predict the future of our planet. That's a pretty big responsibility.
It's a daunting task, but a vital one,
I bet.
because by understanding the forces that are shaping our climate, we can make more informed decisions about how to protect our planet for future generations.
It's inspiring to see how these abstract symbols can have such a tangible impact on our world.
It really is, and it's a testament to the power of human ingenuity and our kind of relentless curiosity to comprehend the universe and our place within it.
Totally. So as we wrap up this deep dive into the world of equations, what's the key takeaway for our listeners? What's the big aha moment you want them to walk away with?
Well, I think the most important lesson is that equations are so much more than just formulas on a page.
Right.
They're powerful tools for understanding, for prediction, for creation.
Well, they're the language of the universe.
It's true.
And they have the power to unlock these extraordinary possibilities.
It's like learning a new language, one that allows us to communicate with the very fabric of reality.
Exactly. And as we continue to explore and master this language, who knows what incredible discoveries await us? What new technologies will emerge from these equations? What profound insights will we gain about the universe and ourselves?
It's a future brimming with wonder and possibility. And it's a future that we're writing right now with the power of equations.
So the next time you encounter an equation, don't shy away from it.
Right.
Embrace its elegance, its power, and its potential to unlock new worlds.
Who knows? You might even be inspired to discover the next world-changing equation yourself. And on that note, we'll wrap up this deep dive into the incredible world of equations.
It's been a pleasure. We hope you've enjoyed the journey and come away with a newfound appreciation for the elegant and powerful language of mathematics.